This lecture, we'll talk about microcontrollers in a little bit more detail. Specifically, we're going to talk about the storage elements, how you store data inside a microcontroller. Some of this is important for us just to have an idea of what type of elements there are inside a microcontroller. And not just inside a microcontroller, really, but also the memories outside the microcontroller, because these are important parts of the system, right? You always have data, you need to store it. So we need to know a little bit about that. So first, here's a picture of taken out of a data sheet for an AVR Atmega 2560 microcontroller. This Atmega 2560 is not the same as what's in the Arduino, but it's, or not in the regular Arduino. In the Arduino Uno, it doesn't have this. Actually, I think there is an Arduino that uses one of these. But this is the same series of processors that you find in an Arduino. And here's some of the information that you would find right on the front page of the datasheet. 8-bit microcontroller, up to 16 megahertz, that's the clock frequency. 256 kilobytes of flash memory, so that tells you something about the type of memory in there. Flash memory, as you may know, it's a type of memory that it's non-volatile memory. So after you lose power, when you regain power, the memory is still there. So you see this in thumb drives. Thumb drives are basically flash memory. EEPROM is also another type of non-volatile memory, similar to flash. SRAM is your regular random access memory. We'll talk about that. And then peripherals are, that's sort of a general term for all the other components inside the microcontroller on the chip, like the timers, A to D converters, and all those other things. So it's got a number of peripherals that I didn't list. I didn't put the whole data sheet up there. But that picture right there shows you what the pins look like. So actually where they are configured on the chip. So that means if you bought the chip, then which pin corresponds to which function, and they're all labeled right there. Actually, this is just a snippet of it because we couldn't put all the pins on this one page, but that's like the upper left-hand corner of the chip. It shows you the pins that you can see there, and there are a lot more pins than that, but they're all labeled with names that are referred to later in the data sheet. So let's talk a little bit about the storage elements that you find in these microcontrollers. Storage elements are basically elements that store data. And there's a need for a lot of data, so you need to store data. A variety of types of different data. You can store data, you can store the program itself. The program itself is data, right? So that has to be stored in some sort of storage element as well. And there are different types of storage elements. There's a speed-performance trade-off. So some types of storage are very fast, but they cost more. Usually they cost more because of area. They take up a lot more area on the chip, so they cost more. Where on the other hand, there are other types of storage elements that are slower to access, but they cost less. They're much smaller on the chip. There's also a power trade-off that I didn't mention here. So, most basic storage element, fastest storage element is a register. A register, it stores only a single value. Now, depending on how many bits wide the register is, it stores one number. So if you have a 32-bit data path, you'll typically have 32-bit registers. So it can store one 32-bit number. It might be a stores whatever you want, one 32-bit number. Maybe the location in a certain memory location, the value in a location in a memory location, or some number that you're working with, some variable you're working with right now in the program, something like that. Very fast. So when I say very fast, the access time is a lot less than a clock cycle. But it's expensive, so you can't have too many of them on chip because they're so big. So there are several special purpose registers that are devoted to particular tasks on the microcontroller. Like the program counter is a common one. Program counter is the register that tells you what instruction you're executing in the code. It's the address of the instruction you're currently executing. So that's something that you, as a programmer, shouldn't be manipulating. You shouldn't be touching that. But it's a special purpose register. But there are also a set of general purpose registers that your program can actually use for computation, arithmetic, things like that. There's also a register file. A register file is basically a group of registers put together. So these are commonly how registers are organized inside microcontrollers. It acts like a memory, just a very fast memory, right? You can only read one or two of these registers at the same time, but usually you don't need to read more than two in a particular clock cycle. Their instruction operands are stored inside register files. So what you're seeing there is an add instruction. Add R1, R2, R3, or 3, R2, R1. It's not going to look like that to you. That's what the machine is actually running, the simple instructions that the machine is actually executing. We'll talk about that a little bit later. But notice it has these operands. So R3 is the destination register. That's the name of a register, R3. And R2 and R1 are the two source operands, the two things that want to get added together. So what this instruction does is it takes the contents of register R1, contents of register R2, adds them together, puts the results in register R3. So commonly, these microcontrollers are reading data out of registers, putting results into registers. Because they're fast, you want to work with registers all the time if you can. Can only read one or two at a time. And you can contain, typically a register file often has like, say, 32 registers. That's very common to find in a microcontroller, 32 different registers that you can access. So that gives you a hint as to how expensive they are. 32 isn't much, but that's generally all you can afford on a microcontroller. Memories. Now memories are, you know what a memory is, it stores data, but memories are made to store a lot more data than registers. So you won't just have 32 registers. Memories will be a lot bigger. So there are varieties of memory. One type of memory is called cache memory. Cache memory, it stores a lot of values. Just to give you a ballpark on how big a cache typically is, you know, this is all ballpark for right now, but let's say, you know, a modern processor, maybe you got a 1 megahertz cache. Oh, 1 megahertz, 1 megabit cache. That's ballpark, but say you got a 1 megabit cache, and that can be plus or minus. But that tells you something about how big they typically are. So usually they're a lot bigger than register files, but they're also slower than register files. Where a register file, you could access that in a fraction of a clock cycle. A cache typically takes you a clock cycle to access, a full clock cycle, which is pretty good, but not as good as a register file. Still fast and expensive. They're cheaper than register files, but they're more expensive than larger memories. So that's a cache. And that's on chip. You would find that on the same integrated circuit as the microcontroller. Commonly in the microcontrollers that we're using, they're what's called a Harvard architecture. So you'll have two different caches, at least two. You'll have a data cache and an instruction cache. The data cache holds the data that the program is operating on, and the instruction cache holds the actual instructions of the code that's being executed. So it's common to separate those two. Now then there's also main memory. Main memory is like cache, except it's bigger and cheaper and slower. So you can see the pictures right there of main memory. That's a typical main memory. If you've ever taken your computer and installed memory into your desktop, you'll get something that looks like what you see in the picture. And you can plug it into a slot inside the board. So it's very big, gigabytes of memory, not in the CPU. So it's not on the same chip as by the way, CPU, again, I'm throwing in another term. By CPU, I'm using that the same as a microprocessor and the same as a microcontroller. Okay, same thing, roughly. So main memory is not going to be in the CPU, it's off the CPU. It's on the same board, but it's a different chip, different set of chips. In fact, if you look at that memory, it's multiple chips, right, all put together. It's connected to the system, connected to the CPU via a system bus. So the system bus is basically a group of wires that are basically drawn onto the circuit board, the printed circuit board, that connect the main microcontroller to the memories. Memory access is slow relative to the cache. So what that means is that in a cache, you might be able to access a cache in 1 clock cycle, right? And main memory, maybe you have to wait 100 clock cycles to access a main memory. So again, that's ballpark, but that's not unrealistic at all. There's what's called the von Neumann bottleneck, which is the fact that in a von Neumann architecture, the data and the instruction are all put into the main memory. And the problem is that main memory is much slower than the processor. So main memory, like I say, maybe you wait 100 clock cycles to access something out of main memory. So if you say you want to do an add instruction, you want to add two pieces of data that are in main memory, you're waiting 100 clock cycles for that data to show up. And then the add itself takes 1 clock cycle. So all your time is going into memory accesses, right? Or it can go into memory accesses. And that is why people use caches, so that to avoid this von Neumann bottleneck. So the von Neumann bottleneck is the bottleneck to accessing main memory. It's the fact that the memory, it's much slower than the processor. So to avoid that, you basically use the cache. You try to rely on the cache and the registers as much as you can, so that you don't have to go to main memory. Now, all these complexities that I'm talking to you about, are you accessing the cache, the register, the main memory, a lot of these we will not be dealing with in this class, because we'll be writing code in either C or in Python. And so all these details about where the data is going to be, is this register going to contain this variable, or is the variable going to be in cache or main memory? All those issues are dealt with by the compiler, if it's C, C++, or the interpreter, if it's, say, Python. So we are not going to have to worry about this level of detail as much, but it's important to understand the difference in the different types of storage elements and how they act and how fast they are, how slow they are, so on. Thank you.